Hey everyone, today we are starting Chapter 9, and as you can see, Chapter 9's title is Extending Perimeter, Circumference, and Area. So you can imagine that we're going to be working with a lot of formulas, a lot of shapes, and I am going to turn in my book and get you to turn with me in your book, please, to page 589, which is Lesson 9-1. Lesson 9-1 is developing formulas for triangles and quadrilaterals. So let's get started at the top of that page. This lesson, oh, sorry, there goes the phone. I apologize. This lesson, and I'm trying to stabilize this a little bit, is a little longer than some. I think it's about 4 pages. So I'll move through it as quickly as I can, but obviously it's going to be several videos. All right, so here we go. Why learn this? You can use formulas for area to help solve puzzles such as the tangram, and they're talking about the tangram to the right. So this shape has been made out of a square. It's been taken apart, all the pieces that made the square, and made into this duck or swan, or maybe swan. I don't know, what do y'all think? All right, the next paragraph tells us a tangram is an ancient Chinese puzzle made from a square. The pieces can be rearranged to form many different shapes. The area of the figure made with all the pieces is the sum of the areas of all the pieces. So in other words, if you knew the area of each piece and you put them all together, added them up, their sum would equal the area of this figure. Also, if we knew the area of the original square, and if the original square was made up of all of these pieces not overlapping at all, then the sum of all these pieces, or the area of this shape, and the area of the original big square made from all of these pieces should be the same. All right, let's look at postulate 911, which is the area postulate. And I'm going to try to turn my phone and see if I can get you a better picture right there. There we go. The area of a region, so that would be like the big square, is equal to the sum of the area of its non-overlapping parts. Let's look at that for just a second. Let's see if I can find a spot to draw a picture, maybe up a little. There we go. All right, so let's say we had a big square. I'm going to have to draw it rather small, but let's say it's a big square, and it's made up of this piece and this square and another triangle right here and maybe a trapezoid right there and a rectangle right there, or we could even make that rectangle into 2 triangles. So as you see, that's lots of different parts, and this postulate tells us that the area of this big square or this region is equal to the sum of the area of each of these non-overlapping parts. So what that means is that this square does not overlap with this triangle does not overlap with this triangle, it does not overlap with the trapezoid does not overlap with this triangle, and the same with the last triangle. So if we knew the sum of this, we could add them up, get their sum, and it would match the sum of whatever this square was if we knew, let's say, that this was a side of 4 and this was a side of 4, and the area of the whole square equals side times side, or 16 square units, then each of these areas independently should all also add up to be 16 square units. So pretty cool stuff. We'll be using that in a fun way near the end of our lesson. The next thing I want us to talk about is recall that a triangle with base B and height H has an area of, I hope I didn't say triangle right there. I'm going to start over on this sentence because in my mind I feel like I might have said triangle. Recall that a rectangle with a base of B and a height of H has an area of area equals base times height, or B times H. You can use the area addition postulate to see that a parallelogram has the same area as a rectangle that has the same base and height. Let's look at that. Let's look first at the one right below the phone. Here we have a rectangle. Its base is B, its height is H. Now they want you to compare that to the parallelogram beside it, but I'm going to cover over the discolored piece, and you'll understand why in just a second. So now here we have a parallelogram. You're just looking at the parallelogram beside my pencil right here, and its base is B and its height is H. And yes, that is a doable height because it is perpendicular to the base. I don't know if you can see the right angle mark right there, but there is one. What they want you to see though is that if you cut off the triangle on the left and rotated it and moved it to fill a spot on the right, now we would cover that up because it's gone, and now we've made that parallelogram into a perfect rectangle with the same base as before because the base was not affected here. Do you see that the length of each is still the same? And the same height. So now our base times height for this rectangle is the same, going to produce the same area as our base times height for the parallelogram. So that's neat. Now let's look at, actually that's not on this page. I'm sorry. I thought they showed us a trapezoid there, but they don't. That's the next page. All right, so let's look at the area of a parallelogram. The area of a parallelogram with a base B and a height H is area equals base times height. That's what I just proved to you, that you rearrange that parallelogram. You cut the triangle off one side and put it on the other, and it's just like working with a rectangle. So again, area of a parallelogram equals area equals base times height. So that's pretty easy to apply. Just remember that your height always must be perpendicular to your base. Okay, let's move down a little bit more. Remember that rectangles and squares are also parallelograms. The area of a square with a side S is area equals side squared. And the perimeter would be side plus side plus side plus side, or 4 side. So that's just a little reminder to you as we move forward. So just quickly going over that again. The area of a square is side times side, or side squared. The perimeter of a square is 4 times the side, or side plus side plus side plus side. All right, moving on. I think that I will stop the video here before we start our first example.